Ever wondered how we predict where a thrown ball will land, or how fast a car will be going after hitting the brakes? It all comes down to understanding motion, and thankfully, physics gives us powerful tools to do just that, the equations of motion. These aren't just abstract formulas. They're the keys to unlocking the mechanics of our everyday world. At their heart, the equations of motion describe how objects move when they experience constant acceleration. They connect 5 fundamental quantities: displacement, initial velocity, final velocity, acceleration, and time. Mastering these equations means you can analyze and predict the movement of anything from a falling apple to a speeding bullet. Let's define our key players. Displacement, often denoted by S, is the change in an object's position. It's not just the distance traveled, but the straight-line distance from start to finish, including direction. Initial velocity, U, is how fast an object is moving at the beginning of our observation. Final velocity, V, is its speed at the end. Both are vector quantities, meaning they have both magnitude and direction. Acceleration, A, is the rate at which an object's velocity changes. If an object speeds up, slows down, or changes direction, it's accelerating. Finally, T represents the time interval over which the motion occurs. Our first equation is perhaps the most intuitive, V warnarf U plus at. This equation directly links an object's final velocity to its initial velocity, acceleration, and the time it accelerates for. It tells us how much an object's speed changes over a given period. Imagine a car starting from rest at a traffic light. If it accelerates at 2 meters per second squared for 5 seconds, what's its final speed? Using the equation, V 0 plus 2 ms2 5s, which gives us a final velocity of 10 meters per second. This equation is perfect for calculating how fast something will be going after a certain amount of time. Think about a skateboarder pushing off. If they start at 1 ms and accelerate at 0.5 ms2 for 4 seconds, their final velocity will be 1 plus 0.5, 4, sugar 3 ms. It's a straightforward way to track changes in speed. Next up is S operature ut plus 1 2 2. This equation helps us calculate the displacement of an object when we know its initial velocity, acceleration, and the time it's been moving. It's incredibly useful for determining how far something travels. Consider a ball dropped from a height. Its initial velocity is 0. If it falls for 3 seconds due to gravity, which is approximately 9.8 ms2, our acceleration A, how far has it fallen? Plugging in the values, S ohms 0.3 plus 1 2 9.8, 32. This calculates to a displacement of 44.1 meters. This equation is vital for understanding projectile motion, or the distance covered by a vehicle. If a train starts from rest and accelerates at 0.2 ms2 for 60 seconds, the distance it covers is S 060 plus 1 2 0.2, 602, which is 360 meters. It accounts for the increasing speed over time. Our third equation is V2 RER U2 plus 2A's. This one is a lifesaver when you don't know the time, but you have information about initial velocity, final velocity, and acceleration, and you want to find the displacement. Or, conversely, if you want to find a velocity given displacement. Imagine a car braking. It's traveling at 20 ms and needs to stop. Final velocity 0 ms. If its brakes provide a deceleration of 5 ms2, how far will it travel before stopping? Using the equation O2, 202 plus 2, 5, s. Solving for AS gives us 40 meters. This equation is particularly useful in scenarios where time isn't directly measured or needed. For example, if a rocket accelerates from 100 ms to 500 ms over a distance of 1,000 meters, you can use this equation to find its constant acceleration. It's a powerful tool for connecting speed changes to distances. Sometimes you'll encounter a fourth equation, S hars 1 part 2 U pupsas T. This equation is derived from the others and is particularly handy when acceleration is constant, allowing us to use the average velocity. It directly relates displacement to the average of the initial and final velocities over a given time. Think about a runner who starts a sprint at 0 ms and reaches a top speed of 10 ms in 4 seconds. How far did they run? Using this equation, s ash 1 2 is 0 plus 10. 4. This gives a displacement of 20 meters. It's a quick way to find displacement when you know both initial and final velocities and the time, i.e., this equation is often used when the acceleration isn't explicitly given, but can be inferred from the change in velocity over time. It simplifies calculations by using the concept of average speed for uniformly accelerated motion. It's a great shortcut for certain problems. These equations are incredibly versatile. When an object is in free fall, the acceleration a becomes the acceleration due to gravity, g, which is approximately 9.8 ms2 downwards. Remember to consider the direction of motion when assigning positive or negative signs to your variables. If an object starts from rest, its initial velocity u is 0. If it comes to a stop, its final velocity v is 0. If an object moves at a constant velocity, its acceleration a is 0, simplifying the equation significantly. For example, if a is 0, s sagt ut. When tackling problems, always list the known variables and the unknown variable you need to find. Then, choose the equation that includes all your knowns and the single unknown. Practice is key to mastering these equations and recognizing which one to use in different situations. The equations of motion are more than just formulas. They are the fundamental building blocks for understanding how things move in our universe. From designing roller coasters to predicting satellite orbits, these principles are at play everywhere. They provide a clear, concise, and powerful framework for analyzing motion with constant acceleration. By understanding each variable and how they relate through these equations, you gain the ability to predict, analyze, and even design motion. Keep practicing, keep exploring, and you'll find that the world of physics becomes incredibly intuitive and exciting. You now have the essential tools to decode the dynamics of motion.